Good morning. My name is Bob Boucher. It's with great delight I'd like to introduce Dr. Micheal Pollock. He's a research fish biologist at the Northwest Fisheries Science Center and the National Oceanic and Atmospheric Administration, commonly known as NOAA. As an ecosystem analyst, Dr. Pollock has been studying watersheds and fluvial ecosystems for more than 2 decades. During his time, he has engaged in research on the influence of beaver habitat on coho smolt production and ecosystem function, and the importance of riparian forests in maintaining stream habitat. Dr. Pollock also provides policy analysis to parties interested in understanding the potential effects of proposed or existing laws, policies, and regulations on our environment. He is co-author of the Beaver Restoration Guidebook, which I'd recommend to everyone as an excellent resource for how to enhance beaver habitat and how to pay attention to what's going on. Thank you, Dr. Pollock.
Thank you, Bob. Can you hear me okay? First little sound check.
Yes.
Okay. Great. All right. Well, great to have everybody here. Great to be presenting and talking about beaver and fish, two of my favorite subjects. And I just one of the things about working with people in the beaver world is it's a really great and fascinating cast of characters. So if you're new to this or attending and interested, I can assure you that your interactions with the people involved are going to be very good ones. And we're going to be talking about beaver, salmon, and trout, but also, of course, people, a big part of the equation here. So probably seen this. This is from a publication, just to give you a sense of, we put out in 2003, just to give you a sense of the distribution of beaver. This map's actually out of date. Beaver have since moved northward into the Arctic, and so they're expanding. And then found evidence of middens in Florida, actually about halfway down the Panhandle, indicating that beaver were there historically, and then parts of Mexico, northern Mexico, and such. So as we gather more information, we're finding that they're more widespread. And then in Europe or Eurasia, they were pretty widespread historically. They're making a comeback, but they were in the Middle East historically. So it's interesting to see there's hieroglyphs of beaver and things like that in the Tigris, Euphrates, Mesopotamia, and such. So, and then this, we talked about what were streams like, what have they been like historically, and I went back and I was kind of interested in how long beaver have been around. Look back at the historic evolution, really not historic, but the evolutionary history of beaver and Salmonidae, which includes includes salmon and trout, and then looked at the compiled a number of studies showing the temperature changes in the last 60 million years or so. And it's a little bit of a complex graph, but what you can see in it is that temperatures, this is log scale, by the way, but what you can see is temperatures have been fluctuating since the Eocene, and they've dropped down generally over time, and then more recently they've been fairly stable. And to the right you can see, I don't know if you can see my pointer, but you can see here there's been a relatively stable period, and that's where civilization has evolved, and then now we're launching off into this uncharted territory that might exceed anything. Some of the models are predicting it may well exceed anything that's existed temperature-wise in the entire time that both beaver, that's Castoridae, and then Salmonidae, so the beaver, trout, and salmon have evolved and existed in the history of the planet. And in this, you can see the hemispheric, the southern and northern hemispheric ice sheets. They weren't around early on. They've come into play and kind of gone back and forth, expanding and contracting over the course of the Pleistocene and Pliocene to a certain extent. And so what we've got here is just kind of an overview of how long beaver have been around, and I'm going to contrast that in a minute with how long humans have been around, and particularly in the context of how long humans have been altering streams versus how long beaver have been there and such. And it's to give a real sense of the length of time that they have been around relative to our meddling in streams. Another thing about beaver is that when you go back, you look, well, how long have they been building dams is an interesting question. And the North American beaver and the Eurasian beaver, looks like from genetic evidence that they split about 8 million years ago, and they both build dams. And so it's indirect, or pretty good evidence, I would say, that the dam building behavior likely evolved 8 million years ago or more, and obviously tree cutting and swimming prior to that. It's possible that they both just on their own learned to build dams, but it seems unlikely. So let's go to the next slide. Just to give you a little bit of historical perspective, that sort of end up putting into words some of the stuff that what you just saw, that the Castoridae and Salmonidae first appeared in the Miocene about less than 30 million years ago. The modern species about 3 to 8 million years ago. You see beaver ponds in the Pliocene about 3 to 5 million years ago, and then they diverged 7.5 million years ago. And both are dam builders. And just to give you a sense of how things have changed over time, and relative to the scale of humans, there used to be some large beaver around. I often get asked, were those giant beaver cutting trees and building dams? And the evidence suggests that they were not, that they were more like kind of hippopotamus and stuff wandering around eating aquatic vegetation and such. So it's possible that they were, but no one's ever found any real evidence of that. And then just to give you a sense of rivers as a whole have been around much longer than beaver or salmon. They've been around for literally billions of years. And I just provide this because in the context of what humans have been doing, and in particular, vegetation has been modifying rivers for about half a billion years, and then we talked about beaver, really, sort of 5 to 8 million years, and then humans, really a short period of time. Graphically or visually, if you think of this as 100 million years of river evolution, and these are deposits of river, the white, the light, those are deposits, river deposits over the course in this geologic record. But relative to the 100 million years, the amount of time humans have been modifying rivers equates to a grain of sand on the top of this very tip top here. So I don't know if that helps, but it's just we're really newcomers to the river management scene, I guess, is one way to think about it. And what have we been doing? So I just want to go a little bit over that and think about beaver restoration. This is about beaver, but we have to look at it in the context of how we've modified the habitat. So I refer to these, how we've modified it as hydraulic civilizations. They appeared roughly 10,000 years ago in very rough numbers. And we started building dams, we started draining, building irrigation canals, we started building levees, we started hardening banks, we started straightening channels, and then all of that created incision, that is, streams cutting down well below their natural or normal level, and that caused floodplain disconnection and such like that. So I think you got some of that earlier in the previous session, for those of you that attended that. And then I just wanted, kind of for fun, just to compare us, the human engineers, versus beaver, the beaver engineers, I guess, and sort of in terms of experience. If they had a resume and we had a resume, they've got about 5 million years of experience building dams. We have about 5,000 years, and our dams are quite a bit different. A number of important things. One is that beaver dams tend to be passable to fishes, just shown here, the difference, the size of them and stuff like that. So there's a number of differences. I think you guys can imagine all the ways that they're different. But it is important to note here on the right with this beaver dam, this is from Eastern Oregon, a kind of desert region, that there are multiple areas where water's flowing during high flow. And we see this as a common feature. And those are used by fish, as we'll see later, to get over them. In terms of canal building and canal navigation, again, we've been doing that for about 5,000 years, beaver about 5 million years. So, and it's just important to point out, people think about beaver dams as a key component, and they are, of what they do to the ecosystem, but the canals are also important, and they provide habitat for fish and other species, and help to kind of diversify the landscape in other ways. And then drainage, we've been draining again for about 5,000 years, and to the lower left here is just this is the Sacramento San Joaquin Valley in California, and it's just this incredibly high network of drainage ditches. Here's a field in Iowa on the bottom where there's these drain tiles, and it's just incredible, the density. And this is just one example, but this is showing the drainage. And this is the for those of you that don't know, this is what is done to a lot of farmland, and I forget what the percentage is in Iowa. It's very high. There's a lot of swampland in there initially, but it's essentially putting in sort of French drains, a subsurface drainage system. You dig a trench to make sure that you have something lower elevation for the water to pour into, and then you drain it all out. And so any water that goes in there, instead of being a wetland, it becomes arable farmland and produces the crops that we all eat. But beaver haven't been doing that. That's not in their resume. And then stream restoration, we've really only been at stream restoration for about 100 years, and beaver have been doing it again, 5 million years, their version of it. Significant differences here. This is a photo, it's from Google Earth. Ellen Wool provided it though. And it just shows how beaver approach habitat modification. And this is a stream with the river, the flow going from left to right. And you can see just numerous dams throughout here, numerous channels, open areas. And what they've done is they've taken the stream and used it to create a wetland stream pond complex across the entire valley. That contrasts with to the right, when we do stream restoration, what we tend to do is create a very, typically a sinuous stream, very controlled. We put in natural looking features now, such as root wads, but the way they're structured, they're generally what we call root wrap, instead of rip wrap, root wrap, and they're designed to be stable. And so we created this stable channel design that is really intended to convey water and sediment in particular through the reach, and not, if there is any flooding, it's very temporary, kind of, it goes up to the surface here and then drops back down into this channel. So we're creating these channels that are essentially in size. They're not very functional in terms of creating habitat, and they don't do things like very groundwater recharge and other important ecosystem functions. They don't do that very well. And we're evolving our thinking and such. So that's not some of the more cutting edge restoration is different, but this is a kind of typical restoration project, but not too many years ago. And then this is just this is from splash damming, a shot of Oregon where it's been extensively mapped. But there's other things that we've done to the landscape that have altered it and sort of change our perception of what a natural landscape would look like. Splash damming is a widespread and long-lasting legacy that has occurred all over the Midwest, all over the West Coast. And it's a pretty brutal practice. You build a dam, you cut down all the trees upstream, push them into the river, and then you blow up the dam with dynamite, and you create this giant flood full of trees. And so all the trees and everything just come pouring down the stream, and of course it just scours out and rips out vegetation and everything. And prior to doing that, the crews would go down and try to cut out and remove anything that they thought might interfere with, for them, getting their logs to market. And so there was a lot of stream cleaning and scouring, and the impacts are significant and widespread. So, and then also in here, there was also in more of the coastal areas, but larger rivers like the Mississippi, Missouri, there were de-snagging efforts. So all this wood that was in the stream, that was all pulled out, creating, again, incision, creating navigable waterways, obviously, but also removing a lot of obstructions in the stream. And so overall, our overall impact to streams has been to remove obstacles, whether they be wood jams, wood or beaver dams, and really create sort of our modern stream, which is not one with a lot of obstacles in it. And I just point this out, that globally, and we have drained a lot of streams primarily for farmland, but also just by poor land use practices. It's significant in terms of the loss of water that's stored on the landscape. If we assume 1 meter of drained landscape, which is very conservative on arable lands, just on arable lands, not on range lands or any other places where there's incision, that's 12% of the annual global discharge. A more realistic number is probably 3 meters on average of these areas. That's 36%, or about a third of our global annual discharge. So just to give you a sense that when you do something on a piece of property to make it more arable, to be able to grow crops, and then you take that and you apply it to a global scale, it becomes a significant problem, especially in the context of climate change and drought, increasing drought and such. So we're in the process of rethinking whether we want all these incised streams incised, or whether we want to try to aggrade them. And a lot of my work has been to use beaver to reverse this drainage, landscape drainage or incision, and to try to benefit ecosystems, or have better uses of ecosystems, and sort of a more conservation-oriented approach towards our natural resources. This is from a paper in 2014, just showing the incision cycle. What you see is a stable sort of dynamic equilibrium in the upper area, and then some event. It could be natural, but in our case, in the last couple hundred years, they've mostly been human induced. You get a channel confined, it starts to cut down. Then once it's cut down, it starts to widen, and you go through this cycle. And again, I stress that there's a geologic record showing this process occurring. And so you go through this, it widens, and then it slowly starts to aggrade again, and you eventually get back to where you were, or on your way to where you were. But that's sort of the cycle of incision and aggradation. And the thing to note is that incision can occur very rapidly, widening can occur relatively rapidly, but then the aggradational process, that is a very slow process. So recovery and under natural conditions, the geologic record suggests, can take a long time. So a lot of interest in what can we do to speed up that process. And we started advocating for, or experimenting essentially, with beaver dams and what are now called beaver dam analogs. I started a project in Bridge Creek, Oregon, and we were just trying to stabilize beaver dams, and we started pounding posts into them. And then we got the idea of putting these and weaving willows together and creating our own beaver dams, which then allowed us to create kind of more controlled experimental conditions. And we did that. The short of it is that we, I'll show you some of the data, but we were able to reverse incision on a scale of sort of years to decades. I was amazed at how quickly we could take an incised stream and sort of accelerate that process of widening, but not widening too much, because the more you widen, the more sediment you need to fill the thing up. And we were able to get pretty good functional ecosystems, sort of shown here in this cartoon form, A, B, C, D, E, F, the sequence. We're kind of able to get to E I don't think we've really gotten up to F yet, total recovery, but we were able to do that in a fairly short order in some places. And so pretty remarkable and rapid tool for accelerating the recovery of incised streams. And this is just a reminder that not all streams suffer from incision. This is work from the East Coast from Walter and Merritt's paper from 2008, an excellent paper if you haven't read it. Really kind of changed the way people think about restoration for a number of reasons. But here I'm just using it to point out that on the East Coast, there were a lot of mill dams rather than splash dams, but mill dams that they used to generate, to create mills. The water needed to run a mill. And in that process, those dams accumulated sediment such that the natural condition was buried down here. In the lower left, it says pre-Holocene colluvium and alluvium. There's carbon dating and such. And to figure out that at the bottom is where the natural stream was, and the top had been since about 1850. Well, they did a lead test, but but by 1850, that there had been an accumulation of sediment over the top of it. So a different problem there. And I think Dorothy is she's worked to excavate material in that case to try to get back to this natural PD system. The other point of this is that their data show that the natural condition was a very peaty, rich organic material on the bottom, and a lot of evidence of beaver dams and beaver and wetlands and meandering streams and such. So again, a kind of a complex habitat that was very wet at the surface. This is just a shot from from a paper we did. It came in PLOS One in 2018, and really just briefly to show that one of the problems with beaver. Here on the left is beaver dams are illustrated in prime beaver habitat is in red, and then the under layer of pink is and then orange and yellow are all the areas where there's a lot of agriculture and residential land use and such. It's where all the flat land is. And that's where all the beaver are. So there's a lot of conflict here. And this isn't an area, but for those that aren't familiar with West Coast, this lake here is Lake Washington, and this gray area I'm pointing to is Seattle. That's the Seattle urban area. So we're just north of Seattle and Washington. And then we've got all this national forest and public lands up here to the right, shown in green. And it's all wonderful. A beaver could come in there and use it, but they don't because it's steep mountainous area. So areas where there isn't a lot of conflict between humans and beaver are areas that aren't very suitable for beaver or humans for that matter. This is just showing kind of where beaver, I'm guessing you've already got something to this at the last session, but just showing that beaver generally prefer streams with a valley width greater than 30 meters, about 100 feet, bankful width less than 8 meters, and a slope less than 4%. And you can, again, just look at Dick Brenner if you want to look at this more. So I want to jump to coho salmon. And just really the issue with coho salmon, there are ESA listed species, Endangered Species Act listed species on a lot of the West Coast, not everywhere. But what this shows is the survival, the overwinter survival, which is one of the ways that where there's a lot of loss of juvenile is over the winter with floods and stuff. And what you can see here is overwinter survival is on the y-axis from 0 to 100%. And then this is just 22 different sites. And we've categorized them by the habitat type. And what you can see is that ponds, there's a lot of variability, first of all, but on the upper left, you can see that where there's a pond in the system or where it's a pond that they have access to, there's pretty high survival generally, not always, but generally. Again, it's nature, there's a lot of variability. And then there's some sort of intermediate areas. But what you see is if you're in streams that are structurally simplified by logging, where they've, again, cleaned it out, some of the mechanisms I already talked about, But where there is not a lot of structure, and certainly not a lot, if any, beaver ponds, you generally have pretty low survival. And so a lot fewer fish that are surviving over winter to then go out to sea the next year in the spring. Some cases you do have decent survival, 60% survival here. That's generally when it's a calm winter. There's not a lot of storms in the winter, and so there's not a lot of mortality. I mentioned the beaver dams and beaver dam analogs as a restoration tool. Here's just some examples of them, of where they've been put. And so wanted to look at, this talking about, well, do these benefit fish, beaver dams? And the BDAs are really designed. There have been a number of publications. The Beaver Restoration Guidebook goes into it, but they're really designed to mimic beaver dams as much as possible. And from an experimental perspective, they've been very good because it allows you to pick a spot, do a before and after kind of study. So you can look at what it was before, then you put in a beaver dam, rather than hoping that a beaver dam comes into a spot you previously studied. So they help in that way. This is a study we did it's been a long-term study that began around 2003 and carried on into the late 2016 or 17, 18. Analyzing the data continues, but this just kind of shows what the effect of putting in a series of beaver dam analogs is, and then the beaver come in and colonize it, and they convert an area that's sort of a single thread, simple channel into a fairly complicated and expanded wetland and pond area. It's the same shot, just kind of a little bit better view. The contrast is a little better. A little later on. And then the question that always comes up is, well, can fish get over it? We had Omicus, it's a steelhead or rainbow trout, and then there's the seago inversion that we call steelhead. And these are the PIAs are pit tag arrays. And the short of it is, it gives you the river kilometer, right? The green, the orange, and the blue. So here's the river kilometers from the mouth of the river. So by the purple is 30 river kilometers upstream and such. And we just looked at the percentage of fish that were able to that we documented crossing these. And so the first, and there's a series of where all of these are. You can see the restoration implementation, where that occurred. And so the number of fish that could pass where there wasn't really much in the way of any beaver dam analogs. And then we put in dozens of these things. So we're not just talking one or two, but we're talking dozens of them put in. So the beginning of the restoration implementation occurs between the array number 2 and array number 3. That is between the green and the, is that right? Yeah, this is the downstream end. Yeah. So I'm sorry, I'm not explaining this well. The restoration of implementation, occurred at the end of 2009. And what you're seeing here is in the subsequent years following the restoration, that we were still getting approximately the same or even better passage relative to prior to the restoration action, and the number, literally, as you'll see in a moment, hundreds of natural and artificial beaver dams in this area. So we felt like this data indicated that there was, and this is again Weber et al. In 2017, we felt that there was little indication that they were being impeded by these many dams. This is again Weber et al. 2017. The issue of temperature has come up. It comes up repeatedly. It comes up in Wisconsin. It comes up in California. It comes up in Oregon, Washington, Montana, Idaho, New Mexico, everywhere. So this is Bridge Creek, Oregon's on the east side of Oregon, in an area that's very hot. It's considered high desert. It's a desert system, so it gets very warm. And this just to show the treatment reaches what happened. So this is going from upstream, the river, the temperature, a series of temperature loggers from river kilometer 35 all the way down to the mouth. And naturally, what happens is you go from higher elevation to lower elevation, that is from upstream to downstream, temperatures increase. And what we see here is that you see generally that trend, but there's a couple variations, and in particular around river kilometer 30 or 29, where there's a series of BDAs, and it just the temperature plummets. And this is August mean daily temperature, so summertime temperatures. And then you see again a similar effect further downstream, about 5 kilometers from the mouth. So, it's data, it's messy. We would love to have had more temperature loggers, but you can see that the general effect appears to be that where you have a high density of beaver dams or beaver dam analogs, at least in this system, in this desert system, it contributed to localized lowering of the stream temperature. Here's another way to look at it. This is, the temperature data is always complicated, but this looks at the density of dams and trying to get a handle on the density of dams. And in some cases, you've got fall, summer, spring, winter, showing that's at different times of year. And what you, I think, see most compellingly, again, the data are in Weber et al. 2017 paper we put out. Then in the summertime, when you get into high densities, the daily maximum temperature right on the far right decreases dramatically. In the fall, less so. The mean temperatures, which are the middle series of figures, not so much an impact. And then the minimum temperatures, you see actually that those are sometimes the more density, the minimum temperatures increase during different seasons. So more to ponder, but just to point out that there's not a simple, do beaver have a positive effect on temperature or a negative effect? It really depends on what time of year and what issue you're concerned about. But for the primary one of summertime temperatures, which is consistently what we hear is the biggest concern, it appears, at least again in this situation in Bridge Creek, that more beaver dams or beaver dam analogs help to keep the temperature lower. And we think the mechanism is through increased hypereic exchange, which allows more of the water to interact with the ground, and the ground, of course, is cool, and so you have this cooling effect. Again, here we see just the number of dams, give you a sense of the number before and after in each of them. I'm going to skip over that in the interest of time. Oh, we've already seen this. So the question that comes up, and I'm trying to be mindful of our time here, is do they increase survival? Are they good for salmon? And you can look at Bowes et al. 2016, but the short of it was we compared Bridge Creek to a control site, and then we had before and after. And what we can see is that in general, Bridge Creek, it varied, but after we did the implementation, we started to see higher rates of survival for Omicas. Another question that comes up is our beaver dams blocking fish. So this was in Sugar Creek, California, and California's like, that's nice, you did stuff in Oregon, but what about California? Okay, we'll go do something in California. So we did that, set up a bunch of pit tags, A3, 7, A4, those are all pit tag arrays and then we tagged fish. There's a block net we put on the lower BDA. Then we had a release pool, and what we did is we monitored how many of the fish went through each of these pit tag arrays and got back up into the pool, and we above. And so we took them from the pool above. This is coho salmon and steelhead / rainbow trout. And we had several options for them to cross over. They could jump, over through these, or they could swim around over to the right. There's a side channel, so they could just swim around the things as well. It was just kind of the way the system set itself up. So we monitored that. The effect was, were they able to go? Well, this is just the coho. The steelhead were much able to get over easily as well, but this just shows the coho. Day one, what we saw was most of the fish were in the release pool. Day two, we were starting to see movement. And then by day three, the fish had mostly left the release pool, and we started, and then the light gray is the ones that were detected above all of the BDAs. And so by day two, most of the fish had moved. That was the day that they all moved. Most of them were in both the pool in the morning, and then they moved out that day. So it took them a little bit of time to kind of adjust, and then a lot of them left. And then we saw very few in the release pool after that, and we, of course, detected the majority of detections were in the pond above the whole thing. So pretty good indication that they were able to pass over. Interestingly, we looked at different ways they could get over, but the side channels and the jumping were about 50-50 for both species. And this just kind of shows you what they had to deal with in terms of velocities. Those diamonds are just the different velocities that they had to contend with. But they were able to pretty easily jump over. They could go up to 40 centimeters. They jumped over 40 centimeters pretty easily, and the jumping didn't seem to be an obstacle. It seemed like they just, I don't know why some of them went one way and some went another, maybe opportunity, but they didn't seem to be troubled by the dams and were able to get over them. But some of them didn't go around. You could read about that. That was, I think, 2022 paper we got out. Then this is a paper that's in review right now. This is comparing that Sugar Creek site to a control. So sort of a similar study in some ways, but with coho. And what you can see, Sugar Creek is our treatment where we put in ponds. Again, the data is complex, but what we saw is relative to our control in French that we really had pretty high survival rates, a lot, but they're also complicated by drought. And so by 2018, French Creek was doing pretty well. There's also some restoration that started occurring in French Creek, kind of screwing up our study, improving habitat for coho. And then in 2019, sugar went completely dry, and in 2020, it was completely dry. This is this mega drought in California. And so you see that the control was better there, and obviously with no water, it's hard to compare, but we still got some survival in these little, they swam upstream and then back down into the pond. So variable data, but indications are that when there's water in the pond, you can do very well, but you do need water for fish to survive. I guess that's the take-home message there. This is just really a gory table that you don't want to look at, but the short of it is, well, we looked at other stuff like how big were the fish. In general, we saw that in the pond habitat that the biggest fish were bigger. On average, we didn't see as much of a difference, but the big fish, and that's what you care about because those are the ones that are likely to come back. The top 10 were bigger in the ponded area, but not always. And some of the really large fish came out of French Creek, but that was in part because of the restoration that started occurring that was creating some slow water habitat. So a little bit of a complex story, but generally we're seeing positive effects. This is just to show, other people have started using BDAs, and as was mentioned, we put out a guidebook. This just showing work in Triple Creek in Washington, and again, rapid aggradation there to bring an incised stream that formerly had beaver in it. Aerial photographs show that there are beaver in there, then it cut down through land use activities, and then this was able to, BDAs were able to raise it right back up. This is just a plug for another paper we put out recently, Ciotti et al. It's a bioscience paper, sort of outlining our evolving thinking about this, and really how to use energy, and to be energy conscious, and to be thinking about working with the existing energy of the system, whether it's solar energy or fluvial energy, stream power to restore streams. I think I'm going to skip through. Well, I'll just tell you what this is, and I'll provide the slide. But in terms of decision making about how to manage beaver and stuff, I just put this out here that we have at least in Washington, a criteria for determining which information is the best available science, and this requirement to use it. And we go through a series of steps and say what's best, peer review, a methodology paper, et cetera, et cetera. So I think we're running out of time, so I'm gonna just buzz through the rest of these. But I encourage any state to be using a process for determining what is the best available science, and to do that. And here's the guidebook. There's some other ones that were mentioned, and I think let me leave you with this, that we're talking about restoration in general. My feeling is the United States is really falling behind. We tend to kind of focus in on really small scale, reach level projects in general. China, other countries, Egypt, they're looking at restoring massively changing weather patterns and restoring ecosystems at a scale that just can't be imagined here. China's restoring the Loess Plateau. It's an area about the size of Belgium, just to give you a sense. The Sinai, they're talking about regreening that, a huge area, and they're looking to the historic record and saying what used to be here, and can we manipulate weather patterns, or is there a way to do this? So I would encourage us to do that. So are we, Hannah, do we have time? Where are we in this?
So we're a little over time, and we won't have time for questions, but I do think that you gave a very comprehensive presentation, and that the Q&A is open for you if you'd like to answer the questions there. And for anyone who has perhaps additional questions, please feel free to drop them in the Q&A, and Dr. Pollock can answer them while we transition to our next session.
Okay, great, Hannah. Yeah, sorry about running over there.
No, that's okay. Thank you so much for your presentation. It was phenomenal.
Okay, good. Yeah, a lot of info. And Hannah, we are going to provide these, or you're going to provide these on a website. Is that right?
Correct. All sessions have been recorded, and once they're formatted, just for ease and stuff like that, we'll be uploading them to YouTube and sending them out to all attendees and registrants. Yeah.
Okay, great. And I just want to leave you with any questions you have. Shoot me an email. I've put it on there, and I'm sure that information's available. I'm happy to talk about beaver and fish anytime, any day. So thank you guys so much, and great. Thank you for the wonderful work you're doing.
Thank you so much, Dr. Pollock, for your presentation. So right now we'll just transition into, we have a few videos that we'd like to show you from our co-hosts and from sponsors, and then we'll transition into Mike Callahan and Lauren Taylor's presentation on non-lethal management. So thank you so much, and stay tuned.